organizer of second international webinar of Nanoscience and Nanotechnology. The theme was this webinar is exploring the novel nanotechnology and nanoscience for future solution, and this is the requirement of future solution. And my talk on focus on the nanomaterial for sensor design. I am Prakash Yadav, research scholar working under the supervision of Professor Anurag Srivastava, Dean of External Affairs, Indian Institute of Information Technology Management, Gwalior. And if you know about more detail about the institute, just please visit. And this is the first triple IT and fully central funded institute of government of India, Ministry of Education of India. Next. Yes, this is the flow of my presentation. Firstly, I discuss the introduction of the nanotechnology. After that, I go to the brief history and special property of the nanotechnology. After that, what is the meaning of quantum confinement, methodology, and applications. After that, I go switch to my talk on sensors, why need for sensors, and after the classification of sensor, working methodology of sensor applications, and my work on phosgene detection using ZNS nanotubes and fluorpectin detection using ZNS nanotubes. After that, I conclude my talk and acknowledgement and references are there. Firstly, we understand what is the meaning of nanotechnology. Nanotechnology is just a science to manipulating the atoms and molecules to build any particular materials. If you arrange atoms in a particular order, a periodic order, then you get beautiful lattice structure. This is the beauty of nanotechnology. What is the building block of? We understand what is the building block of any material. So atoms are the building block. As you know, that atoms are the building block of any material. Just like a atom have a nucleus, electron of in nucleus, atom have neutrons and protons, and electrons are rival nucleus. And when we are talking about the molecules is just not nothing. They are when two atoms are forming and make a desirable output or make a desirable molecule structure, just like H2O and oxygen O3 molecules, then we can say that this is the molecule structure. Maybe it may be poly non-amorphous crystal structure, but molecule have their unique properties. And nanotechnology is not limited into the physics, chemistry, biology, engineering, and material science. It is cover all the field and it have a big umbrella. Firstly, we understand what is the meaning of nano and how it is small. When we what is the meaning of nano? Nano is a billionth of meter. Means 1 nanometer equal to 10 to the power minus 9 meter. And we know that atom size is 0.1 nanometer. That is around 10 angstrom. When we arrange that 10 atoms side by side, then we can make up around 1 nanometer. And here you clearly see the gold nanoparticles, same image, and approximately there are the 10 nanoparticles in 1 nanometer scales. And if we compare the nanomaterial with our hairs, then it is around 15,000 to 1 lakh nanometer in a diameter. This is the so small. And if we compare this at a nanoscale by 10 12, then it is around 10 to the power 8 nanometer. So this is the meaning of nano. After that, I discuss what is the meaning of nanomaterial. If any nanomaterial have a range 1 to 100 nanometer, at least one dimensional, then we can say that these are the nanomaterials. But the nanomaterial classifications are divided into 3 dimensional on the basis of 3 dimensional. What is the meaning of 3 dimensional? Dimensional means atoms are confined or in one direction, 2 direction, and 3 direction. Then we can say that this is the 0D, 1D, and 3D nanomaterials. Let me discuss first 0D nanomaterials. In this type of nanomaterials, all the 3 dimensional are the confined into the nano scales. Means atoms is confined all the 3 directional. No axis, no particles are free to move around anything. particles are moving around this confinement region only. That's why we can, nanoparticles, colloidals, and quantum dots are the example of the 0T nanoparticle. After that, I discussed 1D nanomaterials. At least one dimensional is beyond the nanoscale, and two dimensional are the at the nanoscale. When we are talking about the nanoscale, the nanowires and nanorods, we clearly see uh, we expand the nanowires and nanotips or nanorods in one dimension. Means z direction we expanded uh, uh, before the beyond the limit of nanoscale, but we cannot expand the nanowires and nanotips other two dimensional. That's why we can say that this is the 1D nanomaterial. After that, 2D nanomaterial, any two dimensional are beyond the nanoscale, but at least one dimensional confined it at the nanoscale, then we can set this is the 2D nanomaterial. We clearly understand we have a seed. We expand we expand the seed in x direction and y direction infinitely time. But we have z direction is constrained at that particular seed. So that's why we can say that this is the 2D nanomaterial. Plate light shape in nano layers and surface coating and thin films are the example of 2D nanomaterials. And 3D nanomaterials are the in this type of nanomaterials, all the three dimensional are the outside the nanoscale, but the composite materials means base materials should be nanomaterials. So just like a cluster of the nanoparticles, a bundle of the nano ribbon and nanotubes are the example of the 3D nanomaterials. And we take one example like a graphite. Graphite is the two layer of the graphene. Means we graphene is the 2D structures. When we superimpose one layer on the other layer, top on the graphene layer, then we can get the graphite structures. So this is the also example of 3D nanomaterials. Let me discuss history. We know that nanomaterials are not new. Our ancient are using ancient time. We have a lycra curve, which is made by the gold and silver nanoparticles. But what happens when the light is reflected through this glass, the color is green. But when the light is fully transparent, to this glasses, then we see the red color. So this is the beauty of the nanomaterials. And that time they didn't know this will happen uh, by due to the nanoparticles. And another example is Middle Age. We clearly see we have a window pane of the church, and they show the multiple colors due to the nanoparticles. And in 16th to 17th century, an extremely strong yet flexible Damascus squad was made using the carbon nanotubes and iron carbide nanowires. They usually strong at a from the top to hill. It will be bended. Means very flexible and very strong materials by using the carbon nanotubes and iron carbide. And yes, optical properties is also changes. Michael Faraday have made some nanoparticles, prepared a red gold nanoparticles. We know that the gold particle has bulk gold particle have a yellow color, but when we made a nanoparticles, then we gold color have a red color, and it is stored at the Royal Institute in London. And another scientist G. Mai is also explained the change to why change the color of glasses to reducing the size of nanoparticles. Here we clearly see when the particle size decreases from 16 nanometers to 20 nanometers, the color is changes due to the scattering of the light. And R.A. Geomoselli is study the optical properties of gold and other nanoparticles, and he received the Nobel Prize in Chemistry in 1926. And this is right side of example, you clearly see wavelength and versus excitation efficiency. When the particle aggregated, means bulk particles have aggregated, then excitation coefficient, the peak is very broad and not sharp peak, but and it is shifted through the red shifter. But when we making the nanoparticles, the peak is also sharp. So we get that sharp peak, and it is shifted towards the blue shift. That is the beauty of nanoparticles. There is a famous scientist, Richard Feynman, told his speech, there is a plenty room at the bottom in 1956, and he gave a idea of nanotechnology and the possibility and potential of the nanomaterials. And today we see everywhere in nanoparticles and nanomaterials, and everything is changed due to the nanomaterials, and we get the compact size of the transistor due to the nanomaterials. The famous quote with Jordan E. Moore is also a co-founder of the Intel Corporation, made an amazing prediction at that time. They said that the number of transition on the chip a given area will be double every 1.5 years, and that is the size of the transistor is also decreased 2 times every 1.5 years. And his prediction is today transistor will be 1 to 2 nanometer in the size, and this is true. Intel make the transistor is around 4 nanometer. I mean, Intel make the processor, they have transistor size is around 4 nanometers. And there is a challenge when the nanomaterials is size of the nanomaterials, when the Intel is make the transition around in atomic era, means atomic size of the nanoparticles, sorry, with particles, then what will happen? There is a quite challenging. The quantum tunneling is when we know about the electron is tunneling from then the size of the bit is very less than the electron tunnel from one place to another place. That is the quite challenging talks. And let us see what happen in future. Uh, this is the PPT where we clearly see what is the difference of bulk and nanoparticles. Because the properties is also changes when we compare to the bulk and bulk to nanomaterials. The material is drastically changes. Here I take as example of zinc oxide nanoparticles. In previous time, we clearly see we have a sunglasses, sunscreen creams, and they protect the UV lights. But what happened that time, because they use the large Jordan nanoparticles, they have scattered the visual light. That's why the screen, they leave the spot like a white spot, and skin is not beautiful, but people are using due to the product with their skin. But when we use in sunscreen in nanoparticles, what will happen? It blocks the UV radiation, but what happen? The wavelength of visual light is does not scatter. That's why we clearly see the transparent skin. So this is the beauty of nanoparticles, and also the mechanical and electrical properties also changes when we compare to bulk and nanomaterials. If we are talking about the carbon nanotips, then it is 100 times stronger than the steel, and very flexible and unique properties, electrical properties we obtained by using the nanomaterials. And what is the reason behind these properties? One is the first reason is the increasing the surface to volume ratio. Means what happens if we are taking the 1 centimeter cube, it has a 6 centimeter surface area, 6 centimeter square, sorry, 6 square centimeter area. But when we divided them and by half, then we clearly see that the surface area is doubles, means 12 centimeter square. And again we divided them, the surface area also increases. But then what will happen? Because we get the larger surface, means we have the larger number of particles at the surface. That's why interaction is much that's why interact any materials to interact or any molecules to interact on the surface, the possibility is increased, and flow of the charges, the number of free charges are also increased. That's why the properties are differ. And here we clearly see the activated carbon have their specific surface area, and graphene is also have their specific surface area. But what will happen? So the activated carbon, we are using the filter as a filter, water filtering. In nowadays, you are see activated carbon are using to filter, because it have a porous structure. Means porous, what is the meaning of porous structure? It is store the more contaminated other elements. That's why we are using it in filtering the water. And graphene is also we are using in supercapacitor in battery. This is due to their surface, specific surface area. And another reason is this is the again properties in right side. You are clearly see on a graph. If the particle size is, if the radius of the nanoparticles is decreases, then the surface to volume ratio is also increases. What will happen? What is the reason? Because if we are talking about the corner student, let me to take an example. If you have a student and one student is seated at the corner of the classroom, then it have a few neighbors, but then the center student means it has less interaction to the neighbors. But center atoms, center electrons have interact the more, and that's why when we are talking about the bulk nanomaterials, they have the smaller uh, uh, and free electrons. But when we are talking about when we are talking about the surface area is increased, then what will happen? The interaction the interaction of neighbors will increase due to the most of the electrons on the surface. Another example is the surface tension. Yes, this is the because the surface tension, due to the surface tension, the surface energy is high. This is the another possibility of nanotechnology region. And third is the size effect. Yes, this is the one important properties, because due to the size effect, the chemical, thermal, mechanical, opticals, electricals, and magnetical properties drastically change. In this image, you clearly see if we are talking about their melting points. Okay, then we clearly see gold particles have it melting points around 1300 Kelvin. But when we are decreasing the gold particle size, then we clearly see around 14 angstrom of the gold particle size. It will be made in 300K Kelvin. So this is the beauty. If the nanoparticle size is decreased, then surface energy is also increased, but melting points of the decrease. And we know that the heat transfer mechanism only the two region. One is the lattice vibration, and the second is the free electrons. This is the possible due to if the more free electrons, then the heat transfer is very fast. This is the quantum confinement. This is the another property of quantum confinement. When the length of the particle, we know that when the length of the particle is reduced at same order as the wave packets, uh, quantum confinement is occurs, and in this image you clearly see quantum wires, and quantum dots are the example, and their dots, the corresponding dots are presented. If we are comparing the DOS to bulk particles, then we clearly see the probability of the finding electrons is larger area in 3D images. But when we are talking about the quantum well, then we clearly see 2D quantum well is the 2D structures, but we get the like step like the density of states means the probability of the finding the electron in grand boundary means the probability of the finding the electrons is increases. That's why the quantum well 2D quantum well. And similarly, when we are talking about the quantum bias, then we get the spike like density of states means the number of finding the probability to finding the electron probability is the surface area is reduced, then we get the more possibility to finding this particular electron in this particular region. And if we are talking about the quantum ball, then we get the like a drag delta peaks and molecular type of mm, density of states. Next is this is the another possibility. Quantum confinement, the size of the nanoparticle is decreased, then we clearly see the band gap also increased due to the quantum confinement. In this image, you clearly see the bulk particles have a continuous band structure. continuous band structures. But when we are going to the particle size is decrease, then we clearly see we get some molecular type of structures, uh, band structures, and the shifting of the band is also here. That's why we clearly see the band gap are increased due to nanoparticles. This is the quantum dots. Any question?
Prakash Yadav for very fundamental aspects of nanomaterials.
So this is a big. This is not
Properties.
last slide. Yes.
Characterization. Yeah. You know very well, we do have this nanomaterials for centuries, but only with the.
Can I go for?
Yeah.
Yes, yes. Yes, can I go proceed?
Yadav, can I ask a question?
Yes, yes, no problem, sir.
I expected to see the sensing applications of nanomaterials, as your title said. But said
yes, yes.
anything related to sensing? Why you were focusing on, of course, you are focusing on fundamental aspects, properties, characterization, wonderful. But I also expected to see what are the new sensing applications, for example, gold, that you have discussed. Can you please tell me some new applications of this upcoming nanomaterials in sensing application? Yeah.
Sir, in next slide, I will discuss what is the nanosensor, and I discuss my birthday. If I have 5 minutes, then I will discuss.
You mean to say you will continue?
Yes.
Acha, acha. I thought you have completed your presentation. That is
No,
why
no,
I
no,
asked.
no, sir. But actually, some noise is created. That's why I asked if you have any question.
Acha, acha. Sorry to interrupt you.
Okay.
Think to see some applications, sensing applications of gold and other exotic nanomaterials. Thank you. I'll look forward. I'll wait.
Okay, okay. Thank you, sir.
Yes.
Okay. This is the another the quantum dots. I explained the quantum dots. This is the beautiful example because we know that in the previous television LED they have the RGB colors, but at that time that LED the color is the color wavelength is superimposed, and that time we need the filters to provide a particular color of screen and make them. But when we are using the quantum dots and we clearly see here there is no overlapping of the colors. So that's why we see the in this time of quantum dots LED. The image is very high resolution image. This is the due to the there is and we don't need any filters to get that. That's why the cost is also decreased due to this quantum confinement. Let me, I go to the direct my sensor slide because time is constrained. This is the sensor. We know that what is the meaning of sensor. Sensor is a device to detect and respond some type of inputs, physical inputs. What will be the inputs? Light will be the inputs, heat, motion, moisture, force, and displacement are the inputs parameters. And it will be produced at output signals just like electrical, mechanical, and temperature, and it will be digital or analog outputs. And we know that human have a five different type of the sensor. We have eyes that detect the lights. We have ears that detect the sound intensity, low and high. It will be detect. And we have in the tongue that test the chemicals and any materials. And we have a nose that test smell the chemicals and other things. And we have a skin that detect the pressure and temperature. Then human is the less with five different sensor. And in this time, no sensor are available to match this preciseness as a human-less sensor. And why we need the sensor? Once we choose the sensor, we require this parameters. What is the range of the sensor? Means how they, it means what is the lowest concentration it will detect and what is the highest concentration it will detect. This is the range of the parameters, and then you know that what is the range of my sensor. Then it will be detect a small changes. If your sensor is detect a very small sensor, if my sensor is detect big big change, then it is not useful for very particular application. Then we need to the small. It is possible that our sensor is detect a small changes, and how sensitive it is being again required. If I change the input parameter in one time, then how much that sense and output sensitivity it will be changed. It will be detectable or not detectable. Uh, that is the necessary. How accurate it is. This is the another aspect. Is our sensor is measure accurate or not accurate. This is the desirable. We need to the take it. This is the accurate or not, and how precise the reading is. The output the sensor is give us. What is the preciseness of this sensor that could be asked, and the time taken of the response, how much the time taken means. Suppose you have a sensor, if you want to the measure the temperature, if that it take the measure the temperature around 5 minutes, then it is not useful for me. I need to the sensor, it will be so that temperature in within the instant time. So this is the again what is the time taken to response of the sensor. This is the another possibility. And what is the output type? Is the output signal is the analog signal or digital signal? So this is the another challenges, and you need to know about your sensor. What is the output of your sensor? And environmental factor is also if we are using the sensor in to measure the high temperature and low temperature. While my sensor is work or that temperature or not, that is the environment challenges you also need. Calibration is required or not required, you also see. And the range, wide range is controllable or not controllable by your sensor. It is the another challenges you need to the see before the selecting sensor. And another is the need for external power sources. If you have means your sensor have required the additional power, how much of power requirement you need to know about your sensor, and it is compact or not. What is the cost of the sample? Means if it is compact, it is easy to use a portable devices. But if it is very large and not compact, then we cannot use in portable devices. So this is the requirement you need to understand when you select the sensor. And classification of sensor, we have a multiple type of sensor: chemiresistive, electrochemical, piezoelectric, field effect transistor, capacitive, optical sensor, and their response is different. Suppose you have chemical resistive type of sensor, then you change, you measure the change in the resistance, and you have piezoelectric, then you change the what is the output change is the mass, and capacitive you have change in the capacitance, you measure the capacitance, how much the capacitance is changed by this sensor. Then electrochemical forces, the change in the electromotive forces and currents, and also field effect transistor is, depends on the work function, and optical sensor, you know, the absorption, reflection, and this type of outputs possible for the optical sensor. And this is the again energy consumption. If we are talking about the ME sensor, so we require the high power because of the it have been required the micro sensor, and its operating temperature is very high. We require the greater than 200 degrees centigrade to heat the heaters, and the power consumption is very high, around 100 to 400 milliwatt power is required to operate this sensor, this type of gas sensor. But when we are talking about the self-heated gas sensor, there it depends on the materials. we don't require the external heater, but we require the voltage, and we require the less amount of the power consumption, micro volt to nanometer in nanowatts require the power consumption bit of this operate this sensor. And RT gas sensor in this type room temperature sensor will not require the external heater, and it is operate on the room temperature. So when we are talking about the gas sensor, so we want to develop the room temperature type of gas sensor, but it is not possible due to their another chemical have their certain property, and they treat according to them. This is the working principle of sensor, and here in this image you clearly see there is the sensor cap and hydrophobic filter. What is the use of the hydrophobic filter? The use of this hydrophobic filter is to protect the dust particles and humidity of the environment of my sensor. And this is the again sensor body, and we have electrodes, and again we have metal our sensor on the surface substrate. We have silicon based and heating metal inside the metal oxide surface, and we have a bias, and we put our samples this side. Black side is the you have your materials. What happen when you are talking, when you want to detect any gas, then it interact with the your surface metal oxide particles, and due to this interaction there is a chemical reaction. The conductivity is increased or decreased due to the this interaction, and how much the conductivity changes, how much the resistance it changes, it will be detected by the your output. It will be measured by your output device, and you say that this is the detection of my gas sensor, and you require the sensitivity, check the sensitivity, because what is the meaning of sensitivity? Your sensor is uh, how much sense means minimum 1 ppm is detectable by this sensor or not, you need to check. And these are the applications of the sensor. Now I discuss my work, phosgene detections. Because we know that the phosgene is the toxic gas, and it is used in agrochemical chemistry and uh, isocyanate segments, and it will be used the pesticides and other adhesive lubricants from industry. Majority of spray agents we are using the phosgene and its derivatives. So that's why detection of phosgene gas is also important. And the helping impact of the phosgene gas is also, if the exposure of the phosgene gas is less than around 25 ppm per minute, then it is not harmful for the human. But it is when the exposure is the increase, the percentage concentration of the phosgene in increase in the environment, then it will be very uh, hazardous material for gas for the humans. You'll see around 1,300 ppm per minute, the mortality rate is 100%. So this is the very toxic and dangerous gas. And another is the chloropicrine. Chloropicrine is also usable material, and it is very we use various applications such as agriculture, chemical vapors, and industry. Chemical in industry we use the chlorpectin to produce chemical production, synthesis of the chemical compound, pesticide production, soil fermentation, crop production, pest control also, and chemical war agents suggest like a tear gas, worldwide one. And recent time Russia and Ukraine war, they use the chlorpectin gas. I use the ZNS nano nanomaterial because it have a high dielectric constant, and it have a high dielectric wide band gap structure, and it is very suitable to detect this particular gas. Uh, this is the methodology to detect uh, this particular gas, chlorpectin and phosgene. We know that there are the different methodology are like side bonding, molecular beam perturbation theory, Hartree-Fock theory, molecular molecular dynamics, and density function theory in Monte Carlo simulations. We have different type of theoretical methods, but here I choose the density function theory. Firstly, I developed my ZNS nanotubes, and after that I optimized it, and after that I determined their property, and I validated this result with experimental. If it validates, then I go to the publication. Otherwise, I resynthesize my particles. And in this image, we clearly see there is a Jacobi ladder of density of functions because in the Hartree-Fock theory, we don't use the exchange correlation function, but other types are uses just like LDA, GGA, meta GGA, hybrid, and double beta. So what it happen if we are want to higher chemical accuracy, high accuracy of the detection, then the computational cost is increasing. So what is the meaning of computational cost? Means we require the more number of servers, and time is also increased. But the accuracy is very high if we are using high computational sources like supercomputer. But to maintain the accuracy and uh, our computational limitation, I choose the GGA, generalized gradient approximation, as a action correlation function, and inbuilt PVE, and to calculate this particular nanostructure. And this is the example of, this is the structure of the ZNO nanotubes. And this is the 1, 2, 3, and 4, 5, 6 are the positions. This is the interaction site, means this particular site, my positive molecules interact this particular ring site. And in this image, you clearly see we have a untopped unoptimized structures, and again we have optimized structures. So you clearly see the unoptimized structures have we take our molecules at minimum positions, at minimum positions in computational simulations when the bond is not formed. But after the optimization, we clearly see the molecules are visible due to the physio-absorption nature. Uh, and the distance is changes, and the structure, side view and front view are given in this slide. Similarly, these are the firstly I calculate the formation cohesive energy by this required because we need to take the stability. If my material ZNS nanotube is stable, then I calculate the other properties. So first I take the formation cohesive energy and calculate the energy is around minus 3.823 electron volt per atoms. So I get this material, this nanotube is stable material due to the larger negative value, and the diameter of the this nanotube sorry, sulfur to sulfur atoms is 0.7 nanometers, and zinc to zinc atoms are the 0.6 nanometers. And there is the buckling. You clearly see in nanostructure there is the buckling. Nanotube there is the buckling, and what is the buckling is the 0.09 nanometer. This buckling is matches with the experimental theory, experimental work. And this is the changes of bond length of all orientation, ABCDE. And this is the again second orientation of the molecule. This is the third orientation of the molecule. This is the fourth orientation of the molecule, and this is the fifth orientation of the molecules. And this is the band structure of the pristine pristine ZNS nanotubes. And we get around 3.17 electron volt band gap of this ZNS nanotube. And the bulk is, experimentally ZNS nanotube, the band gap is around 3.65 electron volt. So this is the under GG estimated, it is verified, no problem. and we have a density projected density of states. In this exam graph, you clearly see we have the S state, P state, and D states of the density of states. Once we interact with the Faustian molecules, then you clearly see in pristine dose, we clearly see around two conduction at the conduction band side. There is no peaks, but when we detect our Faustian molecules, then due to the absorption, we get the larger peak at the conduction band sides, and band gap is also decreased. And this is the again we get band gap and band gap reductions. And in table I show how much the band gap reductions. In this graph, I calculated the ionization energy, electronegativity, electron affinity of my targeted Faustian molecules of all orientation. And you clearly see the position E, orientation E is better for every position. And when we compare the band gap and absorption energy, the absorption energy is quite large for the orientation both position orientations B, but the band gap reduction is very less, and change in the band gap is only 4%, and recovery and charge transfer is also minimum. So I need I cannot say this is the good position, good sensing position for that molecule. That's why I go again second position, and last position, which is highlighted red color. The adjustment energy around minus 0.4 electron volt, and band gap reduction is 50%, and charge transfer is higher, and also recovery time is microsecond, 177 microsecond I got. And I said that I confirm this is the best position to detect the my Faustian molecules. And I want to find the region. What is the region to behind this? Because due to the oxygen and sulfur molecules, and as a chemistry, Professor Neil is very good. They note that why charge transfer is higher at this position, because oxygen molecules have a higher negative, and it want to the attract the charge. So that's why that is the reason I get the higher charge transfer and higher reduction in bandwidth. And this is the electrostatic difference potential graph. And here we clearly see the position E have larger interaction, so the larger interaction of Faustian molecules than other position in you see in graph F. And the conclusion of this work, the conclusion of this work is the chemical sensor for detecting the hazard. It is good for Faustian molecules, and the interaction of Faustian is 50% reduction in the band gap, and it shows the high sensitivity and selectivity. And this sensor exhibits the rapid recovery time of the 177 micrometer at room temperature, and it is suitable for the real-time monitoring. And comparative analysis, the adsorption behavior, charge transfer, dose, and electronic properties validate the sensor efficiency. And this is the good if you want to develop a device, then it is good material. Then how much I have time?
Yeah, doctor, thank you very much for your presentation, Dr. Prakash Yadav.
Let me please give me 2 minutes. I finish.
Yeah, sure.
I remove this. Yes.
Sure. You can continue.
Yes, acknowledgement. I want to just say grateful thanks to ABU IIITM for providing the exceptional research in infrastructure and supportive information. I sincerely thanks to my professor, my supervisor, Professor Anurag Srivastava, for his invaluable guidance, insights, and encouragement. I heartful gratitude to Dr. B.S. Bhushan sir, IIT IIT Allahabad for providing valuable scientific discussion. I deep appreciation to Professor Rajiv Ahuja, Director IIT Ropar, for his continuous support. I heartfelt gratitude to Professor Appara, Salmans University, USA, for providing the valuable research guidance. And I acknowledge my collaborative contribution, my research teammate for the Advanced Material Research Group. And lastly, I acknowledge and appreciate to the institute for providing this study. And this is my contact information. If you want to know, then please contact me. And these are the reference. And now, over from my side.
Yeah, thank you, Prakash Yadav, for your wonderful presentation. So, if you are having any questions, please ask Dr. Prakash Yadav.
Prakash.
Yes, sir.
Thank you very much. Very elaborate on the fundamentals of nanomaterials to years of nanomaterials. Could you hear me, Prakash?
Yes, sir. I am here.
Very nice, very nice. Nanotubes and theoretical study
Yes,
on
I did theoretical study.
band structure. So nice to see the advanced studies. Only fast gene, or could you detection of other hazardous chemicals like
Yes, sir. I try the hazardous like a CO2, NO2, and also chlorine is also hazardous. And I also try the SO2, F2, F, F2, SO3, F2. I think I didn't pronounce the name, but I know chemical structure, chemical formula of this particular gas.
Performance of similar morph of tubes of gene will be for the detection fast gene. Zinc oxide. So my question is, like, what role the sulfide species are playing? Is it only the band gap alteration and density of alteration? What is the significance of sulfide anion?
Actually, sir,
Yeah.
Yes. When we are talking about the iteration change of the iteration, this is the due to the interactions. When you see the chemical structures, means the chemical orientation of the molecules. If we are talking about the phosgene molecules, phosgene have the I think two chlorine atoms, one oxygen atoms, and one carbon atoms. Okay. So we have the zinc oxide. Sorry, means we have zinc atoms and sulfur atoms. When we are suppose we have near the if we are Cadence is near the chlorine atoms, then the chemical properties is changes, means the interaction of the chemical interaction between the chlorine and sulfur is interaction of the chlorine and sulfur is differ, and due to this difference, the uh, distance means how much the charge of chlorine they have, how much the charge of our genus they have. So the number of charge increases and decreases according to that. That's why we increase the number of states around the conduction bands. This is the main reason. Due to the which particular elements means which particular atoms are interact your car seat. Sorry, your tube. So this is the I think reason.
Thank you. on the road, its interaction with the in polluting terms like fluoride and others. I fully say. Sir, can we do some theoretical studies like which pollutant will be more effectively sensed by zinc sulfide, like based on the uh, changes in density of states of ZNS when we to ZNS, TNT, trinitrotoluene, or CO2.
Yes, yes.
You know, hydrocarbon pollution is another thing. Explosive molecules are also there, TNT and others. Can we bring such molecules close to zinc oxide and optimize the energy of interaction and say
Yes, sir. So
which pollutant will be?
yes, yes, sir. It is possible. We have software, and we can develop and see the interaction, this kind of interaction. But the only change in the band gap and appear number of states appear in the near the conduction band, it is not possible. We need to check another aspect. If the material is the physio chemical is are bound physio absorption, so the physio absorption and chemio absorption. Chemio absorption, as you know, the molecules is attach your surface. Means we need to if the higher energy means we need the temperature to detect this particular material. So we only use single times. If the your sensor is the chemio absorption type of sensor, that's why mostly biological type of sensor are coming only the single time use. But when we are talking about the physio types of sensor, then we are using multiple times. So we need to check this both aspect. If our materials is chemio absorption, the interaction is so the chemio absorption or physio absorption, and also what is the change of recovery time? What is the recovery time of your sensor? This is the again requirement, need requirement. If my recovery time is much higher, then it is not useful for me. I need the ESMA says uh, uh, minimum recovery time is required. That's why this is the another reason. We don't follow see only the change in band gap and number of density around the conduction band. We also take this aspect also. This is the my answer.
And temperature are also parameters, not only the band gap. Thank you. Thank you for the very interesting lecture on advancing materials.
Thank you, sir.